Sets are a collection of elements. I can actually identify the set by listing the elements, or I could define it. Like I said before, all the students in this room, that's a set. If you list the elements, you list them in brackets like this. Capital letters are usually used to indicate a set. This is equal to this. Okay? This set is equal to what's ever in here. At the moment, what's in here? Nothing. When that happens, it's called the empty set. B is the set of a star, a circle, and a triangle. A star is an element of the set B. A square is not an element of the set B. Let's say C is the set that contains a circle and triangle. All of the elements of this set are also in this set. C is a subset of B if and only if all of the elements of C are also in B. A lot of words, right? How about if we just wrote it this way? C is a subset of B. That works. Now, here's an interesting question. Is A a subset of B? That we said that C is a subset of B if and only if all of the elements of C are also in B. If you looked at all of the elements in A, every one of them that you could see, which would be none of them, are also in B. So the empty set is a subset of every set. How about this? Is this true? B is a subset of B. Hold on. Yeah, it is. But it's kind of not really what we had in mind, right? So usually we write this. C would be a proper subset of B. B, not so much. Because, yeah, it's part of B, but it's also all of B.
A quick clarification. This symbol here says that C is a proper subset of B. That means they're not equal sets. That is, there's some element in B that's not also in C. If we want to talk about subsets generally, without promising that we're not including equal sets as subsets of each other, we use this notation.
This is the complement of C. Now, assuming that B is our universe for the moment, the complement of C would be all of the elements that are not in C in such a way that if I put these two together, they would be the whole universe. Complement. This is the complement of C. And it's sort of like a complementary angle where it's, you know, all of the degrees you need to add up to 90 to make a right angle. So whatever's left. In this particular case, if you want to think in terms of complement and what the word really means, it means the set of things you would need to finish off the whole set. If all you had was C, what would you need to complete the picture? That's another way to think about it. All right. Oh, by the way, the empty set is designated by that. This is not the empty set. That's actually a set containing the empty set. But this Greek letter by itself is the empty set. Yes.
What does like the backwards 3 mean?
Ah, this symbol right here is element. It's not so much a backwards 3 as it is a modified E for element. So the star is an element of the set B. So I started talking to you the other day about two words that have meaning in English, and they also have meaning in math, in set theory. Intersection. If you have two roads and they cross, this one is Main Street and this one is Center Street. If I'm here, I'm standing in Main Street. If I'm here, I'm standing in Center Street. If I'm here, where am I standing? Where am I? If I tell somebody to come pick me up, what do I tell them? Right, I'm at the intersection of Main and Center. I'm in that part of roadway that actually belongs to both roads. Okay? That's intersection. And it is designated by that symbol when we're talking about sets. Let's do a couple of new sets. Let's say M and N. Okay? The intersection would be the part that is actually belongs to both of these sets. So in this case, the intersection would be the set 1, 2. Okay? Union. So the two examples I can come up with in English. When you're married, right? Everything that, like, the two people have, everything that belongs to one person and the other person who are getting married, suddenly they pool them together and it belongs to both of them. So if you are a bunch of employees who work for some guy and that guy's not treating you well, and you say to the guy, hey, treat me better. The guy says, or what? You say, well, what, you'll quit? You say, well, no, I sort of need to eat. But then you go back and you say to all the other workers, hey, listen, you know what? If we all got together and collectively said to the boss, treat us all better or we will all quit. That might be kind of powerful. Then that person goes to the boss and says, we have formed a union. And everybody's in. In terms of set theory, that's designated like this. And if I said M union N, in this case here, that would be the set 1, 2, 3, 4, 6, 7. You notice I don't have to list 1 and 2 twice. But all the elements of both sets combine together into one set. That's the union. So that's intersection, that's union. Now, a Venn diagram, actually named after a guy named Venn who came up with this. What if we said this was set M and this is set N? 1, 2, 4, and 7 are all in set M, so they belong in this circle here. 1, 2, 3, and 6 are all in set N, so they belong in this circle here. In order to make that work, I got to put 1 and 2 over here. If I do that, they're in both circles. And then, to fill it out, M is 4 and 7, and this is 3 and 6. Where does 5 go? If 5 were actually part of it, and I asked you, where does 5 go? 5 would go here. Outside. Still inside the universe. If I were talking about the universe of numbers between 1 and 7, Well, 5 would be in that universe, but it wouldn't be in M, and it wouldn't be in N. So altogether, how many numbers are there between 1 and 7? There are 7 of them, and 1, 2, 3, 4, 5, 6, 7. They're all represented here. That's a Venn diagram. This part right here, that part right there is the intersection, the overlap, the place where both roads cross, the place where both circles overlap. This right here is the union, where all of this stuff is in it. Okay? Now, let's say that our universe here, and I'm going to use U for universe, is the set of all numbers from 1 to 7. What would be in this set? Yeah.
1, 2, 4, and 7.
Why 1, 2? 1, 2, 4, and 7 actually is M, isn't it?
3, 5, and 6.
But here, I'm saying we want the complement of it. So we have 1, 2, 4, and 7. The ones we don't have are 3, 5, and 6. If I'm using this as my whole universe here, then the complement would include things that are in here that aren't in N. Okay? Right. So this is my whole universe. The complement of M would include N. If we never defined N, if N didn't exist, then it would just be this circle M with these 4 elements in it and these 3 outside. Okay? Yes?
You know how 5 wasn't originally in the numbers
Right.
that you gave us?
Uh-huh.
If you didn't ask for specifically what is the union between 1 and 7, do we just assume that 5 is already in there? Or like any number that is missing from the original
No.
number?
I specifically defined the universe as these numbers. And notice that I don't have like 1.7 in there anywhere. So it's not all the numbers between. It's not even necessarily all the counting numbers. It's whatever we define it to be. I believe that's everything you need to know in order to be able to start doing this.